All right, so today we'll talk about robot velocity, as I said earlier, because we have the need for speed. As usual, we're gonna have a little bit of background to remember what we talked about last week's and see how they're connected with what we'll do today. Which is basically how do we calculate velocities for the robot. We'll see the distinction between linear and angular velocity. We'll talk about a quantity that we call the Jacobian. How do we invert it? Some ideas on this velocity ellipsoid and so on. Very briefly to remind you what we already know. We talked about transformations. How do we transform from one frame to the other, like coordinates of a point or a pose. And we defined what we call the forward kinematics, which in the case of the robot, it describes the position and orientation of a coordinate frame, usually located at the end effector, with respect to a reference frame. And we do this using these 4x4 transformation matrices, which the 3x3 submatrix represents orientation. Basically how these three axes, one for each column, how these are oriented relative to the reference frame. And the position column, which tells us where is the origin of this frame with respect to the reference frame, right? That's what this 4x4 matrix describes. We'll use it again, that's why I like to keep on reminding you all the details. So yeah, in the grand scheme of things, we covered the forward kinematics. I mean, velocity can also be considered part of the forward kinematics, but I put it separately because it will start going into the inverse kinematics as well towards the end of the lecture. All right, so today we will do this part of the grand scheme of the course. Right, so again, what we've seen so far, we talk about these kind of robots, articulated robots, robot arms, which is basically a mechanism consisting of joints and links. And by controlling, we saw that by controlling the position of the joints, right, we can control the position of the end effector. And we saw a way to calculate this relationship, like, okay, how does the position of the end effector change for different joint coordinates, right? So we control joint position, and that affects the end effector position. Could we do this with velocities as well? Could we find a way to calculate the end effector velocity as a function of what? Joint velocities? What do you think? Obviously, yes. So that's what we'll see today. Why do you think this is useful? Why would we need to have a way to calculate, or why would we be interested in the velocity of the end effector? What kind of, I don't know.
To know the time it takes to do a job.
To do a trajectory, right? Or we might want to control this velocity so that we can execute the trajectory faster or slower. I'm closing this so there is no current. Yeah, because in some applications we might execute something faster or slower. Like in the example in the lab, you will see we have to transport some liquid, and if we do it very fast, maybe we spill it. That's just an example, of course, right? All right, so we're talking about velocities, and before we dive into the, you have a question? No. All right. Before we dive into the details of how we calculate velocities for robot arms, let's talk about velocity in general. So basically here I have some animations where we can see that, okay, segments in the robot, like links, can have linear or angular velocity. For instance, here we have a animation where the end effector of the robot, you see, it just translates relative to the fixed frame, right? So if I just show you the last link, which has the end effector, you see that we just have a translation. So this would be like, I don't know, the linear velocity of the end effector. Or I might have just a rotation. Right? So again, I have now 3 links here, and the end effector, basically the tip of the last link, the red line, does not change position, so it has no linear velocity, doesn't translate, but it just rotates. Right? So this is the kind of velocities that we're talking about. Of course, you can imagine I have scenarios where I can have both a linear and an angular velocity combined. Right? So here in the same example, if I look not at the red segment, but if I look at the green segment, basically moves like this if I isolate it. And we can decompose this into 2 different types of velocity. Right? So this motion is basically the combination of, let me play it again, of a linear motion and an angular motion. Right? So if I add these 2 together, which is basically a translation and a change in orientation, I will end up with a combined motion of that we see for this segment here. Okay. The idea is that I can calculate linear and angular velocity separately, and then I can add them together to calculate the overall effect. All right? Simple stuff. Good. What is linear velocity? What kind of quantity is velocity? Is it a scalar? Is it a vector? Is it a matrix? Hint on the screen. It's a vector, right? What does it mean it's a vector?
It has orientation.
It has orientation and direction. Direction is orientation, right? And what? I didn't hear what you said.
Module.
Module? What is a module?
Amplitude.
Amplitude, right? What?
A value.
A value. Amplitude is a good word. It has a direction, yeah, and a magnitude. That's the proper way. Well, you can say it as an amplitude. Amplitude is usually for, I don't know, periodical things. But it has a magnitude, right? So we have a vector which shows us, okay, towards which direction are we moving? And then, that's the orientation of the vector. And then the length of the vector shows us the magnitude. Okay, how fast is it moving, basically, right? And what we saw already from the second lecture, actually, for vectors is that basically in 3D space, they have 3 components, right? So velocity being a vector, it basically has 3 components, which we can also call them 3 velocities. I know velocity along the x-axis, velocity on the y-axis, velocity on the z. Or we can also think of them as, I have a vector which represents the linear velocity. And this vector has 3 components, basically the 3 projections on the 3 axes, right? So the linear velocity, I will denote it with this v and vector. And the 3 parts of it will be x, y, z coordinates. They have the dot on top because dot is basically the differential with time, right? The derivative with time, sorry. It's called the differential. So then this shows me what is the rate of change of coordinate x, which would be the velocity on x. So how fast is it changing on the x coordinate, right? Or on the y or the z. That's why we have this dot. Can also be Vx, Vy, Vz, different ways to denote it. If I have an object that, let's say, it has 3 different velocities, let's say velocity on x, y, and z, how can I add them together? I use vector addition, right? You probably remember this maybe from high school, right? If I have multiple vectors acting on an object, I can add them together using vector addition. In math terms, it would be adding the individual components on the x, y, and z directions, just add the values. All right? Good. So linear velocity, I have an object, it moves in a certain direction with a certain magnitude. I have a vector representing this information, right? So if an object moves that way, it will be that, you know, whatever direction. What about angular velocity? What kind of property is angular velocity? Is it, when I have something rotating, right? Is it a scalar, is it a vector, is it a matrix? What kind of quantity is it? You know the difference between scalars and vectors? All right, good. And matrices, I hope. So what about angular velocity? Still a vector?
Because it has also orientation and magnitude.
All right, good. It's still a vector, correct. And it has an orientation and a magnitude. So basically, the orientation would be what? What would be the orientation of an object? What would be the orientation of the angular velocity of an object rotating, I don't know, around a certain axis? Trigonometric what? Anti-trigonometric.
Clockwise or anti-clockwise.
So it would be, I don't know, on this figure, let's say, where would it be? How would I draw angular velocity? So this is, let's say, a disk rotating or an object rotating around the center with radius r. Where would the axis of rotation be? I'm trying to find something bigger to show. Yeah. You said something about clockwise, counterclockwise. What do you have in mind?
So we have a reference system and we are considering if the rotation is positive or negative regarding that system.
All right. But you say that angular velocity is a vector, right? Where does that vector point towards for an object rotating? An angle?
We are measuring an angle regarding to the coordinate system.
Okay.
It's tangent to this radius.
It's tangent to this radius, so something like, I don't know, something here, let's say.
Yes.
Like, so if I have an object rotating here, it would be, I don't know, something pointing towards you.
Yes.
This is the tangential velocity, and that's linear velocity.
All right. So that's not it, right? So this would be the instantaneous linear velocity, right? Because, and we'll see that in a while. What would describe the angular velocity of this thing? Let's do, I don't know, a thought experiment. I feel like Einstein now. Let's say I have this object rotating around this point here. Where's this button? All right. And then I have the same object rotating around this button here, the flat one. Would the angular velocity be the same?
No.
No.
Because it depends on the point of the
Axis of rotation, right? So then it makes sense that the angular velocity has some relation with the axis of rotation, right? And that's basically it. The angular velocity is a vector aligned with the axis of rotation of the object, right? So if an object rotates like here around, an axis passing from this point, then the angular velocity vector will be aligned with that axis of rotation, right? If I had a CD, let's say, or a disk rotating around the center, so then the vector representing the angular velocity would pass from its center. Okay? And then whether it would point towards you or towards me, it would have to do whether it's rotating like this or like this, following the right-hand rule. If it would rotate like this, then the velocity vector would point towards you, right? So now I can, if this object would rotate like this, it would point like you, towards you, or like this, it would point upwards, following the right-hand rule rotation. If it would rotate the other way around, then the axis would be below. If it crashes on the floor, then the axis is gone as well. So basically, this is not it, right? This is the place where it should go, and this is basically perpendicular to the disk. All right. So this shows me the direction, whether it's rotating clockwise or counterclockwise, the way you see it. But the right way to define, okay, where the vector will point is using the right-hand rule, right? So if we're rotating like this, then the velocity will point there. If we're rotating like this, it will point there, right? And then, so that's the direction. The magnitude of the vector would be with how fast it's rotating. If it's rotating slowly, it will be a short vector, let's say, with a small magnitude. If it rotates fast, it would be a big vector. Okay? So again, we have a vector, it has a direction and a magnitude. The direction shows me basically what is the axis of rotation, and the magnitude shows me what is, how fast is it spinning. Okay? Since it's a vector in 3D, again, it has three components. Like it's basically the same kind of object as linear velocity. It has, we denote it usually with omega, and it has the three components, omega x, omega y, omega z, which shows me basically how is this vector oriented in space, relative to a reference frame, always. Right, you can also think of it, these individual parts, as how fast it's rotating around the x-axis, the y and the z-axis, and we add them together to get the overall vector. It might be not as intuitive as with the linear velocity, but it's basically the same thing. All right? If I have an object that rotates with two angular velocities, let's say I have two vectors, how can I add them up? Same thing, no problem. It's vector addition. If I have two vectors, I can calculate the combined effect by adding them together. All right? Now going back to what you were discussing earlier about the tangent velocity, basically if I have an object here at this radius, this thing has an angular velocity, but at the same time it also has some linear velocity, because it also translates. It changes position, right? It doesn't only change orientation. Maybe it would be more clear if I draw some, not just the point, because the point is difficult to understand the rotation, but if I have a, I don't know, a remote control, it's rotating around an axis. If it's doing this kind of motion, it changes orientation, so it rotates, but it also translates, because the position of the remote control also changes, right? Since the position changes over time, I have some velocity. So how do I calculate the linear velocity of an object rotating around an axis? Anyone remembers? So it's the, sorry? So it will be angular velocity times the radius. Correct, right? So here, what is the angular velocity units? It's 1/seconds, right? The radius is meters, so meters/seconds gives me linear velocity. If you ever forget what's the right order for this, you can remember. Right. Now this gives me the magnitude of the linear velocity, but we can also get the direction of the linear velocity. So this is not a vector, the way I wrote it. Because if this would be a vector, and this would be a vector, I cannot just multiply them like this, right? Because this would be a 3 by 1, I cannot do the multiplication, right? So if I want to write the vector form of this, so I can calculate, okay, what is the magnitude and the direction of the linear velocity, I use another kind of product. It's called the cross product to calculate this, right? So I have the angular velocity as a vector, which shows me basically the direction and the magnitude of the rotation. And then I have the radius, which is also a vector, right? Because it connects, it's a vector connecting the center of the object with respect to the axis of rotation. Using this cross product, I can calculate basically what is the vector of the linear velocity. All right? You ever heard of cross product before? Probably you did. Short reminder, this is how we calculate the cross product. The cross product is being produced, so it's calculated between two vectors in 3D space. So if I have vector A and vector B, the cross product of these two is calculated like this. So here I will have vector A and vector B. Each one has three components, A1, A2, A3, and B1, B2, B3. And I can calculate the three components of the resulting vector. This would be the first component, the second component, the third component, right? With I, J, K is the three axes. So the property of the cross product, which is also a vector, is that it is perpendicular to both initial vectors. So the A cross product B is perpendicular to A and is perpendicular to B. And its magnitude is proportional to the magnitudes of the in A and B vectors and to the angle, right? When the angle is 0, then the resulting cross product will be 0. When the angle is 90 degrees, it will have the maximum magnitude. Okay? Good. So going back here, basically we can try to verify this relationship that they are perpendicular. I have an axis of rotation and radius, and basically the linear velocity will be a vector perpendicular to the axis of rotation and to the radius, right? And this is working for any orientation, right? You see, when the object is rotating, the radius also rotates, the axis of rotation doesn't change, right? And the linear velocity is always perpendicular to these two, right? Okay. Good. So this is the background we need to start talking about velocities of the end effector, right? And we will calculate again the linear and angular velocity of the end effector with respect to a reference frame. That's the goal. I want to know how fast is the end effector rotating and translating with respect to a reference frame. Right, so we'll talk about the linear with v and angular with omega velocity of the end effector. I should have put vectors there, the arrows, but I forgot. And in the end, we will combine these two vectors into one big vector, having all 6 velocities denoted with this Greek letter. How is this letter called? It's called xi, but I heard everybody says it's zeta, but yeah. Anyway, we can call it how you like. Cheetah is that animal that runs in the jungle. Buenos dias. We call it xi in Greece. Whatever. If you call it cheetah, I'll understand. Anyway, and we call this quantity the twist, because it combines the linear and angular velocity in one term, right? Good. So the approach that we use in order to calculate the twist of the end effector with respect to a reference frame is that we are trying to add the contribution of each joint, because these are the parts that are moving. We are adding the contribution of each joint to the end effector velocity, right? Each joint will have some contribution to the velocity, which will be a vector, right? And then we saw that if I have multiple vectors, I don't know, velocity vectors acting on the end effector, I can add them together to calculate the total effect. Right? So if I have this joint rotating, producing some velocities here, and then this one as well, I can calculate the overall velocity by adding the two contributions. All right? Good. So we'll take it joint by joint and calculate what's the contribution of each joint and then add them together. And we treat first the linear velocities, first for prismatic and then for revolute joints, and then the angular velocities for prismatic and revolute joints, right? Because the effects of prismatic and revolute joints are different, so we treat them differently. And we'll start with the most simple case, right? I have a robot. It has some revolute joints, Q1, Q2, Q3, they're revolute joints, like this, and like this. And Q4 is a prismatic joint. You can think that, something like this, that just translates, right? And we want to calculate what's the contribution of on linear velocity due to translation or due to prismatic joints, right? So what do you think it would be? So here I denote it as Q4 dot, Q dot 4, whatever is the velocity of joint 4. It's a bit hidden, I hope it's visible. But here I have, a vector showing me, okay, that this joint is translating along that direction by some amount, Q dot 4. What do we expect the contribution on the end effector to be? What it would be, it would be a velocity vector. What would be its direction and its magnitude? Just one joint moving along that blue axis. So basically something like this. I have this joint, it has this axis of translation, and it moves up and down. What would be the effect on the end effector? Velocity. It would have the same direction, right? Right. If this joint moves like this, then the end effector will also move like this. This happens to be the last one and also in the example, but you can imagine that if I had the revolute joint, let's say here, this segment, if it would translate like this, then everything after it would also translate in the same direction, right? So the velocity of the end effector would be basically equal to the velocity of the joint, both in direction and in magnitude. Great.
So it is applied when it's revolute joint, this stuff with the...
No. So this is just for translation, so this is just for prismatic joints. We'll see, next slide is for revolute joints. All right, I start with the easy one. So basically we can show that the velocity due to joint 1, so that's what I denote with U1, the velocity of the end effector due to joint 1 is basically equal to Q dot 4, which is a vector, right? It has a direction, right? Which I decompose basically to, why is it a 4 here? It should be 1. Sorry for that. So this should be 1 and 1, 1 and 1. So I decompose it to a vector of unit 1, calling it Z1, which just shows me the direction, right? And the magnitude, which would be how fast it is translating, like this Q for Q1 dot, all right? And I will call this basically JU1 for maybe already apparent reasons. But you can ignore this for now. I'll call it JU1. So it's the J for the velocity, linear velocity, that's why you have U, due to joint 1. Okay? Good. If I had two joints, prismatic joints in this example, I could calculate what's the contribution due to the second joint as well. and then I would have to add them together. We'll see this for the revolute joints, the addition. Good. Clear? So, linear velocity due to prismatic joint is basically given by the axis of translation of the prismatic joint and by the amount of the magnitude of the translation of the velocity. All right. Now, what about linear velocity due to rotation? We talked a little bit before that if I have an object rotating around an axis, it will both change orientation, so it will have some angular velocity, but it will also change position, which means it has some linear velocity as well. Right? So in this example here, also on the screen, I'm talking about end effector velocity due to the rotation, so end effector linear velocity, Ju1, due to rotation around the first joint. All right, so that would be the tangential velocity of, so let's say in this case u1 vector would be equal to what we saw earlier, right? How do we convert angular velocity to linear velocity? If we know, it would be the angular velocity times cross product this radius, which is correct. I'm not putting the things here. Right. Now, what is this radius? So here I have this rotation around this axis. I have this radius. And then I have this basically circular motion, right? Producing this tangential velocity. Great. What is this radius? And maybe visualize it here as well for those that are, more the visual types. So I have linear velocity of this part here due to rotation of this joint would be, shouldn't move, but this should move. It would be given by this axis of rotation, right, times this vector here, this radius. Right? So when I move, let's say, like this, I will have some linear velocity in this direction. When I move, it will be in this direction. Okay. Now, let's start with the radius, since we already talked about it. Like, how do I calculate this radius?
We can use the forward kinetics.
All right. So, what do I need? Oh, let's keep it R1. We need the what?
Translation on the two axes, and then I compute the vectorial sum of it.
One by one. So, what do you say in the first? I didn't hear.
For instance, in this case, if I know it's translated on y by a some amount and translated on x by some amount, the radius would be the vectorial sum of them.
Okay. And somebody said about forward kinematics. So how do we use forward kinematics here to do what your colleague said?
Each joint we can just use forward kinematics to know the coordinates of the end vector, therefore knowing the distance.
Right. So I'll put also a frame here to understand this better. So let's say my robot is here. I have this joint, right? Another joint, whatever. Basically, I'm trying to calculate this vector, right? Which is what? How I wrote it there as well, is this O4, which would be the position of the end effector, in this case. Let's use a different color. The position relative to a reference frame, right? Minus O1. Okay? So if I want to calculate this vector, orientation and magnitude with respect to a reference frame, I need to know where it starts and where it ends. All right, so this is O4, This is O1. And as you might remember, if I call this R1 vector, and these are also vectors, of course. As you might remember, I guess from high school, R1 vector will be what? O4 vector minus O1. All right? Another way, if you don't remember this relationship, is to know that O4 is basically O1 plus R1, right? Vector addition. So if you swap R1 and O4, you can get to this. Or actually you move O1 on the right side. Okay? So in order to calculate linear velocity due to a revolute joint, I need to know this quantity. This quantity, you said that we can get it from forward kinematics, right? That's exactly what we did last 2 weeks. We learned how to calculate the position of this point, of the end effector, with respect to a reference frame using forward kinematics, right? And we kept on saying that we can do this for any part of the robot, not necessarily for the end effector. I can calculate the first joint, the second joint, the third joint, whatever joint, right? So this would be my O1. Like, where is the first joint, the origin of the frame attached to the first joint with respect to a reference frame. Good. What is this omega I? This is the angular velocity due to rotation around a joint. What would that be? It's a vector. It's the vector passing through the joint, showing me the axis of rotation. We saw earlier that the angular velocity is a vector passing from the axis of rotation. So if we know we have a revolute joint that rotates around a certain axis, then omega I will be on that axis, right? That gives me the direction, and the magnitude will be basically how fast the joint rotates, like the, I don't know, degrees per second that I have. All right? So again, this follows the right-hand rule. So if the robot rotates like this, it will point towards you. If it rotates like this, then it will point towards the other side. If it doesn't move, then it's going to be a zero length vector. Great. So I have the linear velocity of the end effector due to joint 1, U1, is the cross product between the angular velocity around the joint, which is basically how fast the joint rotates, which is vector q dot 1, cross product this vector, which is basically the radius of the rotation, right? Which is a vector, so that we get a velocity vector here as well. Right. What is q dot 1? What is the vector representing the angular velocity around joint 1? As we saw earlier, is the axis of rotation, which is this zi vector, times the magnitude. So how fast are we rotating? Okay? So eventually this can be rewritten like this. I can factor out q1 dot, because it's a scalar, and it will not affect the cross product. So it can be left out. So I will have, what will be this, the result of this? I have a vector, cross product another vector. It will still be a vector, right? So I have a vector, 3 elements, times magnitude. If you remember, in the previous slide, we also called this Ju1. So it's some quantity which is a vector multiplied with a scalar, the joint velocity, right? Now, if I have another joint moving, the second one, let's say, it's the same thing. The velocity of the end effector due to, the linear velocity of the end effector due to the second revolute joint will be basically, again, the cross product between the Now this rotation, right? So again, this angular velocity, cross product, this distance. Now I have a smaller radius, right? So obviously I will have a different velocity due to this joint than to this joint. Okay? But the way to calculate it's the same. Now instead of having this radius, I will have this radius. Right, the second joint, or as I saw there, that one. Same idea. I still take the end effector, 04, minus now the position of this joint. Again, this can be rewritten as, so q dot 2 vector is z2 vector times the magnitude q dot 2, right? And obviously I can do this for any joint, right? So this gives me the linear velocity of the end effector due to revolute joints. And we saw how we calculate for prismatic joints. Okay? Good. So this covers the whole linear velocity of the end effector. What about angular velocity? So angular velocity is still a vector. And the angular velocity due to rotation or due to revolute joints will be what? So if I have an end effector rotating, let's say, around this joint, sorry, what will the angular velocity of the end effector due to this rotation with respect to the reference frame, what will it be? How fast is it changing orientation? Basically, and around which axis? Maybe let's see it on a different axis. Let's say this rotation. How fast is it doing one rotation around, I don't know, this axis?
Just as fast as the joint.
Just as fast as the joint. If the joint rotates like, I don't know, once a minute, oops, sorry. The end effector will also rotate around the axis once a minute, right? If it rotates twice every minute, then it will also rotate around this axis twice a minute, right? So the magnitude is obviously related, and then the direction around which it will rotate, now you see it rotates around an axis aligned with this blue, right? If I don't know, move this joint, then it will rotate around an axis aligned with this blue, right? So the angular velocity of the end effector is basically the same as the angular velocity of the joint, right? Which is given by the axis of rotation and the magnitude, right? So here, let's say, the angular velocity due to the first joint will be a vector parallel to the vector, the axis of rotation for the first joint. For the second joint will be a vector aligned with the axis of rotation of the second joint, and for the third joint, the angular velocity will be aligned with the third axis of rotation, right? So basically, omega 1 will be equal to q1 dot vector, which is equal to, again, I decompose it to an axis of rotation with length 1, right, times a magnitude. Right? Omega 2 will be like this, and omega I will be Zi. All right? So this is angular velocity due to rotation. Do we have angular velocity due to translation? We saw that we have linear velocity due to rotation, But do we have angular velocity due to translation? And I see people shaking their heads. Why not?
Because it doesn't rotate, basically.
Yeah.
If we just translate.
If I just translate, I'm not changing the orientation of the object.
0, 0, the left.
Sorry?
The angular will be 0, the angular vector.
Exactly. The angular vector, the angular velocity vector will be 0 because I'm not changing the orientation when I'm translating. Right? I'm still keeping the same orientation. I'm not doing any changes in orientation when translating. It would have been the same if it was here. Right? The whole robot would just translate due to this prismatic joint. If it was, I wouldn't change translation.
Are there any prismatic joints which offer also rotation? For instance, they do like this?
No, because that's not a prismatic joint. The definition of the prismatic joint is that it only has one translation. That's basically a screw joint, what you're describing, right?
Yeah.
Which is rotation and translation coupled. They're not independent, but yeah. Prismatic joints are just translation. All right, so basically, if we have prismatic joints, angular velocity will be a 0. And to keep things consistent, it will be a vector of zeros. Right? It would be 0 rotation around the 3 axes. Right? A vector with 0 components on all the 3 axes. This will be useful when we add things together. Any questions?
On the scheme below you have an n. Is that the number of joints?
If we had n, what?
Yes, it was like On plus 1 minus OI.
Here, right? Yes. So here we have On plus 1. Yes. N is the number of joints, indeed. And it's n plus 1 so that I go to the end effector. So that's the notation I'm using here. Good point, I didn't clarify it. Basically here, in this example, I have 1, 2, 3 joints. So the end effector is O4, right? Because O1 is the first joint, O2 is the second joint, O3 is the third joint, and O4 will be the end effector. So in the general case, yeah, it will be On plus 1, which would be the position of the end effector with respect to the reference frame. Good point. All right, let's quickly see how do we add all the velocities together. We said that the overall velocity will be the addition of the contributions from each joint. So if I have velocity due to joint 1, linear velocity for instance, due to joint 1, and linear velocity due to joint 2, the total velocity will be vector addition of these two, right? Xi. Vector. Okay, so what does this mean in terms of our equations? My velocity of the end effector v will be equal to v1 plus v2 plus v3 vector, and vector addition until n, where n is the number of joints, right? Obviously there is no reason why this shouldn't be the case for angular velocity too. Yes. Before we go to angular velocity, we saw that u1, u2 was basically, we wrote it like this, a vector showing me the direction times the magnitude of the angular velocity of joint 1, or linear velocity, because this is general, like it is both for prismatic and revolute. Here I don't distinguish between the two. It's how I calculate this vector basically, that is different for prismatic and revolute, right? And I can write this in more, algebraic form. I can have a vector of these vectors, ju1, ju2, okay, multiplied with a vector of the joint velocities, the magnitudes. Okay, so these things show me the direction basically, and these quantities here show me the magnitude. And I can write it in an even more condensed form as ju times q dot, right? Where q dot is a vector of all the q dot 1, q dot 2, q dot n being the number of joints, right? And ju being a vector of the individual directions. Right? Obviously, this is the same thing I can do for angular velocity. So angular velocity of the end effector will be the sum of the individual contributions from the joints together, because they're vectors. I can add them together, which we wrote as j omega 1, q dot 1, and so on. And in the end, I can also write it in this form, where I have all the direction vectors and the magnitudes, and I can write it in a condensed form like j omega times q dot up together. If I have these two, I can combine these two vectors. So this will be a vector for the linear velocity and a vector for the angular velocity. I can combine these two in even more condensed form. I compress, and I have xi, which is the end effector twist, which is linear and angular velocity. Here, if you see on the right side, we multiply with the same quantity, which is q dot. So I can multiply both of these with the same q dot, and I will eventually have this big J, which is part of J linear and J angular, multiplied with q dot, all the velocities. I will have the end effector velocity. Okay? This is what we call the Jacobian. That's why we use J. Spoiler, it was, but yeah. This is what we call the Jacobian. And it's basically a map that shows how can we map joint velocities, how fast the joints move, to end effector velocities, right? And it's basically a matrix multiplication. J times q dot gives me xi. One more slide and then we'll take a break. So xi, as we said in the first slides, is basically linear and angular velocity. So 3 components for the linear velocity and 3 for the angular. So that's a 6 element vector. And on the right side we have n joint velocities. Right? What would be the size of this Jacobian matrix? So here I have xi, which is a 6 by 1, is equal to a Jacobian times q dot. Q dot is n by 1, because I have n velocities.
6 by n.
So this would be a 6 by n. Right? How come it's a 6 by n? I'll show you better in the next slide. So I don't go slides back, so after the break. Unless you have questions. You have questions?